Assalamualaikum. My name is Hanisatira binti Roslan, and today I will present for my paper, which is the effect of seismic design on the cost of structural works for two-story residential building. So these are the outline of presentation, starting with introduction and end with references. Thousands of earthquakes strike the earth every year, resulting in faulting, tsunamis, volcanoes, landslides, and liquefaction. The majority of earthquakes strike along the Pacific Ocean Rim because the majority of volcanic activity and earthquakes occur there. It is also known as the Ring of Fire. However, most earthquake-inducing stresses are caused by the movement of tectonic plates. Tectonic plates will shifting as they drift around on the viscous or slowly flowing mantle layer below, causes a tremendous amount of stress on Earth's crust. When the stresses get too large, a system of faults form between the plates. A tremendous amount of stress can build up. The stress is then immediately relieved by huge vibrations known as seismic wave. Malaysia considered as low-moderate seismicity zones. However, Malaysia should not be overlooked and should be concerned mainly in Sabah due to historical earthquakes with magnitude 6.0 and above, such as in Kudat, Lahad Datu and Ranau, which caused damages and fatality. After an earthquake on 5th June 2015 with magnitude 6.1 hit Ranau, Sabah, which lasted for 30 seconds, have opened people's eyes and minds about risk of earthquake. Earthquakes can't be prevented, however, levels of risk can be reduced or eliminated by considering seismic design for future constructions of new buildings. On the other hand, the influence of seismic design implementation may cause a number of challenges related to the building designs, which may affect the structure requirements details. Seismic design is still not enforced for new structures because of uncertainty regarding its impact, particularly on cost. As a result, the goal of this research is to see how different levels of seismicity and soil types affect the cost of steel reinforcement in reinforced concrete residential buildings with seismic design consideration. So these are the Sabah seismic hazard map. There are three objectives in this study: to investigate the influence level of seismicity on the total of steel tonnage, to investigate the influence of soil type on the total of steel tonnage, and lastly, to estimate the cost increment of structural work due to seismic design in Malaysia. These are the scopes of work for this study. Two-story of RC residential building as a basic model. There are two parameters involved, which is the peak ground acceleration and type of soil. The type of analysis that will be used is model response spectrum analysis, ductility class medium as referred to Ir-Code 8, and lastly, the design tool that will be used is Tekla Structure Designer. These are the literature review that being used for this study. From literature review, the selection of the characteristic of seismic design being very important in analysis and design with different parameters. Different parameters regarding this deformity, it is important and defines the overall response of the structure. Majority of previous study used lateral force method, while this study employ design response spectrum analysis. This research work is planned to be conducted based on three phases as shown in figure 5. The phase 1 is a generation for basic model without seismic consideration by using Tekla Structure Designer computer software. But phase 2 is structure analysis and seismic design, considering seismic load based on Ir-Code 8 and National Annex with various parameters. The design will be carried out based on different reference peak ground acceleration and soil type. Lastly, for phase 3 is taking off, which is the process to compile the total concrete volume, area of formwork, and weight of steel reinforcement. Costing process also involved in this phase. Now I will go through for each phases. This phase involves generating typical key plan of two-story of RC residential building in Malaysia as basic model. In the table 3 shows the cross-sectional size of beams and column of RC residential buildings for type 1 and type 2. In these figures show the plan view of key plan for type 1 and type 2. The structure analysis and seismic design processes covered in Phase 2. Both types of model were classed as Category A by Ir-Wan. There are 4 levels of seismicity were represented by the reference peak ground acceleration, and 2 types of soil were taken into account for this study. Based on National Annex, these values represent the seismicity level in Sabah. The activity class median was applied to all seismic models, and the non-seismic model of RC residential building was designed and analyzed in compliance with Eurocode 2 without any seismic design consideration for both types of model. So these are the load specification in Tekla Structure Designer. Overall, there are 18 models with different variables of the RC residential building for 2-story. The amount of concrete, formwork, and steel reinforcement for all RC residential models was determined during the final stage of taking off process. The seismic model findings were compared to non-seismic model results and presented as weight of steel reinforcement per 1 meter cube concrete. The overall cost of materials for structural work was estimated using the standard building material pricing by Jabatan Kerja Raya Malaysia. So these are the standard building material pricing by Jabatan Kerja Raya Malaysia. These are the expected outcomes for result and discussion. The value of fundamental period of vibration can be obtained from the model analysis. For 2-story is 0.5 seconds. The magnitude of base shear force is determined by the magnitude of spectral acceleration at the fundamental period of vibration as shown above. Table 6 shows as the value of reference peak ground acceleration increases with similar soil type, the magnitude of spectral acceleration at the fundamental period of vibration increases as well as the magnitude of base shear force. Thus, different soil type has different value of soil vector as proposed by National Annex. The highest magnitude of base shear force, which considering reference peak ground acceleration 0.16 G and soil type D, which contributed to highest magnitude of design bending moment, shear force, axial load, which result in highest amount of steel reinforcement for the models. For the next discussions, regardless of the design applied in this study, the beams, columns, and slab size were said to be identical throughout all models. As a result, the concrete volumes, the lean concrete for beam and slab at ground level, and the formwork areas for beam, columns, and slab were similar for every model. As a result, the cost of concrete and the cost for the formwork was expected to be similar for each model, regardless of soil type. As shown in Figure 15 and Figure 16, it is clear that the increasing of reference peak ground acceleration tends to increase the total weight of steel reinforcement per 1 meter cube concrete. Otherwise, regardless the value of reference peak ground acceleration, soil type D shows the highest total weight of steel reinforcement for beams compared to other soil type, around 5 to 18% and 1 to 13% respectively compared to non-seismic model. As indicated in previous part, reference peak ground acceleration 0.16 and soil type D models have the largest magnitude of base shear force, resulting in the greatest bending moment, shear force, and axial load. As a result, the models use the maximum amount of steel reinforcement. By regardless the soil type, in Figure 17 and 18, the total weight of steel reinforcement per 1 meter cube concrete for columns with seismic design increases around 5 and 4% respectively when compared to non-seismic models. High value of reference peak ground acceleration 0.10g, 0.13g, and 0.16g shows highest amount of steel to be provided as reinforcement for columns due to seismic design consideration. Figure 19 and Figure 20 illustrate the normalized total cost of structural works for Type 1 and Type 2 models. By considering seismic design, for Type 1 models, increases by 0.62% to 1.31% and 0.61% to 2.16% respectively, while for Type 2 models, increases by 0.24% to 1.22% and 0.20% to 1.71%. As a conclusion, these two parameters significantly impacted the magnitude of the base shear force, thus it leads to highest amount of steel to be provided as reinforcement. Regardless the soil type, as the value of reference peak ground acceleration increases, the weight of steel reinforcement also increasing for beams and columns compared to non-seismic model. The results show that even building with similar structural configuration tends to have different amount of steel as reinforcement. Next conclusion, regardless the value of reference peak ground acceleration, soil type D required higher amount of steel reinforcement compared to other soil type. The results show that the soil type also influencing the total weight of steel reinforcement. Lastly, by considering seismic design, the total cost of structural works tend to increase, for which was influenced by the soil type and the value of reference peak ground acceleration for both types. These are the references in this study. Thank you.